Hello, welcome back to storage structures in operating system. Right. So basically, a computer have a main memory and a secondary storage. Right. So a storage structure basically consists of these two. Right. Now the main memory only large storage media that the CPU can access directly. Right. This is basically usually your DRAM. Right? It's accessed by a random access. They are typically volatile. That means if you turn off the computer, the data itself will be lost. And there's typically random access memory in the form of DRAM on your computer, right? The secondary storage is basically an extension of the main memory that provides large non-volatile storage capacity, right? And we're gonna look at this, right? So this is basically usually could be the hard disk drives or the non-volatile memory NVN, which exists on the newer computers these days to allow faster access of data, right? So the disk, when we're talking about hard disk, the disk surface is basically is logically divided into tracks, which is divided into sectors. Right, the disk is basically a rigid metal or glass platter that contains some kind of magnetic recording material. So within that is broken down into specific tracks and sectors, and the disk controller basically determines how logically how to interact uh, between the device and the computer, right? Okay, so please read about this, some of the definitions or explanation about what are bits, bytes, word, megabyte, gigabyte. Some of you might know it already. It will be a good refresher on what it is. Now the storage hierarchy basically is a triangle relationship here between speed, cost, and volatility. Um, you know, and it usually it's usually in the case where, let's go into this next picture here, where we see that as you go down this hierarchy, things get slower, right? uh, and you can see the relationship here. Registers is basically on your CPU, and then we have a cache which is on your CPU that can keep certain types of data. And then we have main memory, and then we have non-volatile memory. These are secondary storage. This could be hard disk drives and etc. Right? And then we have optical discs and magnetic tapes. Right? These are even slower. Right? But when we look into the the speeds basically gets faster, but the storage also gets bigger, right? The capacity of it, right? The cost, on the other hand, it gets more expensive as you go up, or cheaper as you go down, right? Magnetic tapes are even cheaper today, right? Now the modern computer system works that we have an operating system and we have a cache. Right, so each CPU basically have a cache, and there is a bunch of CPUs. So it's either one CPU or multi-core CPUs, and it will have it will make IO requests, it will have data, it will receive interrupts, and it will work together with the memory, where it will receive instructions and data. So instructions and data basically move from the memory to the cache, right? And cache back into the data, right? And it will receive a direct memory access from multiple devices, right? To access memory at the same time, right? Right. So direct memory access structure, so DMA, right? This is devices that are connected, interrupt basically device controller, right? So direct memory access allows devices to basically access memory without going through the CPU, right? And it's basically used for high-speed I/O devices to be able to transmit information uh, at close to memory speeds, right? So this allows faster interaction between a device and memory, right? Otherwise, you have to go through the CPU to push or move data, right? Now, the device controller transfer blocks of data from buffer storage directly to the main memory without CPU intervention, right? So that makes it makes it faster as opposed to the the early stages of a computer, where data from the keyboard maybe would have to go through and interrupt the CPU, and the CPU basically instructs to push some data into memory, right? That is being keyed into the keyboard. But today, we can access it. Those controller helps in pushing everything that's buffered on the controller straight to memory, right? So whenever the CPU needs it, it doesn't have to go through the device. It just have to go through memory, right? Only one interrupt is generated per block rather than the one interrupt per byte, right? So right, makes lesser interrupts in this case, right? Now, operating system basically starts with a bootstrap program, right? So this would be something like your BIOS, right? Simple code to initialize the system and basically load the kernel, right? So this is what the BIOS do anyway, right? So, or the computer BIOS that basically is a simple code to basically load the kernel, right? So after the kernel is loaded, it starts system daemons, right? Or basically services that's provided outside of the kernel. So this could be your scheduler, your Windows system, your networking, and etc. Right? Now the kernel itself is interrupt driven for all hardwares and the software. So hardware interrupts by the devices would issue hardware interrupts, and the software would basically issue exceptions or traps so that it knows when to interrupt the CPU to do certain things, right? So requests for operating system services comes from what we call a system call, right? And this would allow the computer to do specific things. For example, whenever you want to read a data or file system, right? It will make a system call that would issue a trap or exception to allow the program to access hardware level information, right? Okay. The computer system also, the operating system basically is a multi-programming system, right? So, single user cannot always keep the CPU and IO devices busy. So the idea of a programming is used that allows to organize jobs, code, and data so that CPU is so CPU always has one to execute, right? So it always have a job, right? Otherwise, or most program has things to do, right? So happens because some CPU, some programs while it's running, it might be idle when it's doing some other stuff. So this would make it not efficient in trying to use the program, right? So a subset of total jobs in the system is kept in memory, right? So whatever program that you have, we call it a job, right? Is basically kept in memory, right? But we cannot keep the whole program in memory, so we keep a subset of it into memory, right? So some of these jobs is then selected to run on the CPU, right? And we call this selection is done via a scheduling algorithm, what we call a job scheduling, right? So when a job scheduler basically assigns a certain program to run, right? The OS basically switches its current running program with the particular job, right? So you can imagine that there's a bunch of jobs, and the job scheduler purpose is basically trying to select which job to run so that all jobs pretty much get to run and use the CPU most efficiently, right? There's also an idea of computers are multitasking. Um, is basically an extension of batch systems to switch jobs so frequently, right? So it's basically keep on to allow and to make it feel that all processes are running at the same time, it will basically do a time sharing, right? Instead of letting a program run until something's finished, it basically keep on switching the jobs through a CPU scheduler, right? To do a CPU scheduling instead of a job scheduling that schedules job to run a specific time. It provides a CPU scheduler that basically swap running jobs in and out of the memory, right? In order to do this, it basically needs a virtual memory uh, that programs that are not exactly in memory yet, right? So, because there's a lot of jobs running, right? So some of those programs can be in memory, but some of them cannot. So, in that case, you need to extend the capability of a memory and provides a virtual memory that allows the CPU to access them later and put it into memory, right? Because not all of them fit in memory. So in a multi-program system, you'll see the operating system with some subset of processes that needs to run, and it runs process 1, process 2, process 3, process 4 through a scheduler, right? Basically, right? Um, right. So whenever we decide which program to run, the OS basically has two types of mode, right? We call it user mode and a kernel mode or protective uh, uh, user mode and kernel mode, right? Or privilege mode, right? We call it privilege mode, kernel mode, privilege mode, right? So basically, this allows, whenever we are running OS systems, or kernel specific functions, we call it kernel mode, and then it will allow another program to run, which will switch to a user mode, right? This is to protect the operating system itself and other system components, right? So it does this by setting the mode bit that is exists on the hardware level, right? Okay, let's look at this, right? So when we look at this, when a user process is running, the user process execute and it tries to make a system call, right? A system call, that means it's trying to access something that the kernel, only the kernel has privilege of doing. It will switch from the user mode to a kernel mode, right? So this happens through a system call that will initiate a trap or exception here, right? And it will allow the kernel to run the system call because only the kernel can access hardware level execution, right? And then after doing that, it will return back to the user the results and change it back to user mode. This basically protects from the user accessing the hardware level directly, right? In the computer as well, the operating system as well has a timer to prevent infinite loop or process hogging resources. Right, the timer is set to interrupt the computer after some time period. This is so that we can tell that how long a program is running, and tell the scheduler to regain control or terminate a particular program or basically change to another program, right? So that one program would not be stuck there if something wrong happens, right? So so a part of the operating system, one of the most important things of a program, the operating system is basically trying to do process management, right? Uh, so we have a process, which is a program in execution, and you know, uh, you know, so it's we basically quantify a process here uh, as a unit of work that needs to do, right? So in this sense, a program is a passive entity. So it can be one program that has specific code, and a process is basically an active entity, right? It's a process, they can have multiple process for one program, right? And a process is active, and when it is in execution, right? So it's actually running on the CPU, right? The process itself needs resources to accomplish its task. It needs CPU, memory, IO files, right? Some initialized data, right? So a program is basically do not need all these kind of things, right? Because it's not running, right? A program is just a program, right? A process is basically an instance of that program, right? So a process termination requires reclaim of any of these resources. So if you're already running, right? If a process is already running, it's on a CPU, is using resources, whenever you want to finish it or you want to terminate it, you have to reclaim all of these resources again, right? Now, a process can be single-threaded process, which in the case it has one program counter, uh, specifying the next location of instruction it needs to run. So a program contains a bunch of lines of code or instructions that it needs to run. So a process would run all these instructions, right? There is a program counter that basically tells what next instruction it needs to run, right? And it runs this instruction sequentially one at a time until it is completed, right? A multi-threaded process has one program counter per thread. So, imagine one process but contains multiple threads running multiple code that could be similar, right? But they have their own program counter, and how they process depending on how might be different from one another, right? Because they're different threads, right? Uh, Typically, a system has many processes, some users, some operating system running concurrently on one or more CPUs, right? So it can get pretty complex as the number of processors increase, the number of threads increase, and the number of users increase, and the numbers of CPU increase. So how do we manage all this? It's what it gets more complicated as we advance in technology, right? So the operating system has to be smarter in managing all of these resources, right? So a process management activity basically, create and delete users and system processes, suspend and resume processes, provides a mechanism for process to synchronize, for processes to communicate, and basically to handle any deadlock situations, right? Where, it causes the computer to, the process to hang and not able to progress, right? Uh, the other part of the operating system is doing memory management, right? To execute a program, uh, to execute a program, either all or some parts of the instruction must be in memory, right? So all or some parts of the data that is needed by the program must be in memory also. So this would be the instructions that it needs and the data that it needs, right? Now, memory management determines what is in memory and when, right? So, we have a lot of process to run. We have a scheduler. We might select some of this process. We might take it from a hard disk and put it in memory, right? Some memory is not big enough, so we will choose parts of it, or we can fit all of it in it, right? So this is some of the job of a memory management, right, in the operating system, right? Now, memory management activities basically is to keep track of which part of memory are currently being used and by whom, right? And deciding which processes and data is to move in and out of memory. Remember, we put it in memory or we take it out from memory, because memory is basically a limited resource, right? So we have to take it from somewhere and put it there, put it parts of it as the computer runs, and replace it with other parts that are more relevant during the execution, right? So allocating and deallocating memory space is basically needed in memory management, right? Now, the other part of things that we will it's important to the operating system is file system management, right? The OS provides a uniform logical view of information storage, right? So, data is being kept in data, but how in the logical storage unit, right? It's in the hard disk, but it's kept in a logical storage unit called a file, right? So this is to abstract on how we basically access this low level data, right? So it's not very, we cannot really determine how this data looked like on the hard disk. It's not easy to logically access it. So in order to to abstract this difficulty, we create files and directories, and we have a file management system that helps us accessing files on the device, right? File system management basically, uh, you know, uh, have one of his jobs is basically to use files to organize into directories, have control access to these files. Some people can read, some people can write, right? Uh, so some of the OS activities include creating and deleting them, manipulating them, mapping those files into the secondary storage, and doing some backup, right? So besides the file system management, there is also mass storage management, where we have a bunch of disks used to store data, and how do we manage all this mass storage, right? Um, Now the disk itself is usually slow, and the computer basically manage this in trying to save data or read data from it. You know, uh, whether to figure out what disks are being mounted. For example, when you put your thumb drive into the computer, one of his job is to make sure that this thumb drive is mounted so that it can be accessed, right? And it try to figure out how much free space is available in it, how this data storage is allocated, how this scheduling is being done, trying to schedule data being written and read from it, protect, doing partitioning on the hard disk, which one is drive C, which one is drive D, trying to partition it hard disk into specific partition parts, and then particularly protect it based on user, right? And there's also caching that's important in the operating system, right? Caching is basically performed at many levels on the computer, in the hardware, in the operating system, and on the software itself, right? Information in use copied from slower to faster storage temporarily. Basically, that's the idea, right? We copy, stuff that are being accessed on the hard disk. Because the hard disk is slower, we put it in memory so that we can access it faster, right? Uh, so faster storage are basically kept in cache, and check first to determine if the information is there. So if we cannot find it in the cache, we will look for it in the hard disk, for example, right? Now, so this happens in many levels, and this is to allow us, faster access to certain information and data, right? Cache management is important, and there's many designs of it in order to have access to it faster, right? So cache size and the idea of when we replace a data from the cache is also important, right? So if we're keeping maybe what we call a cache or a stack of items that we frequently use, eventually, because it's limited in size, we have to decide what we want to throw out. So the replacement policy is kind of important here, right? As well, right? So here's are some of the characteristics of various types of storage, right? So registers, cache, main memory, right? So you can see registers and cache are usually on chip, on the CPU most of the time, on the hardware level. And we have main memory, CMOS SRAM, flash memory, magnetic disk, right? So this is probably the last, right? Solid state disk is basically a disk similar to a hard disk, right? So, and memory basically moves from magnetic disk, main memory, cache, and hardware register, right? So this allows, right? So the higher you are here, the faster, but you cannot move everything from here to here because the size gets smaller as you go on, but the speeds gets faster, right? So IO in the operating system also is important for IO subsystems, and basically it's for drivers for specific hardware devices, right? How memory is being buffered, caching, and how do we hardware devices are being used by the users, right? Protection and security, this is also the functions of the operating systems. You you have some identities, you have file identities, group IDs that would access that are able to access certain things on the computer. Would an operating system also provide virtualization, right? To either run multiple applications in different types of hosts, right? So we're going to talk about this more later when we get into the virtualization section, right? Interestingly, today we have all kinds of virtual machine that could run on our own machine so that we can emulate other operating systems. So we can have an operating system inside an operating system, right? That is allows us to run multiple virtual operating system, right? Um, so this is one of the idea. If we have a kernel and we have another operating system, we can have multiple kernels running in one of the kernels here, right? So we create a wholly virtual environment right here, right, for virtualization, right? uh, Operating system also supports a collection of separate possible heterogeneous system networks, right? LAN 1, metropolitan area man pan, so all of this works basically on the TCP IP stack, and you know and how we access data, particularly on the network, right? So next is we're going to talk about the computer system architecture, and we're going to stop here for now, and I'll continue with the following slides in a bit. So I'll see you then, right? See you again. Bye bye.